Welcome back, everybody. I hope you've enjoyed your study of sequences and been able to work some problems and get a handle on what type of issues we have when we're talking about sequences. And we're going to move on to series now. So essentially, when you take the terms of a sequence and add them together, you get what's known as a series. So let's head over and get started. Okay, so we're talking about series. And I want to start with this motivation. We'll come back to it, but let's suppose that a patient requires a daily dosage of a certain drug. The amount present in the bloodstream after T days is given by DE to the negative KT, where K is some positive constant. What is the limiting amount of the drug in the bloodstream? And so in other words, you've got your daily dose plus what's left from previous days, okay? And you know that this E to the negative K causes decay, right? Which is good, right? You want whatever's in your bloodstream, that blood or that drug, to eventually leave your system. But does it ever fully leave your system? And what is that limiting factor? And so we will come back to that. But first, let's get some terminology out of the way. So given an infinite series, so where you're adding infinitely many terms, we can talk about partial sums denoted by S subscript n, which says just to add, instead of from 1 to infinity, add from 1 to n. And the sequence will converge if the sequence of partial sums converges to S. So notice that the partial sums form a sequence, right? I mean, I could look at S1, S2 will be the sum from n equals 1 to 2 of an. S3 would be whatever the sum from 1 to 3 of an is, and so on, right? We get a sequence. And so all our issues of convergence can be applied to the sequence that's built from those partial sums. Let's look at an example. This is known as a telescoping series, and you may not see why yet, but you will shortly. And so we want to investigate some partial sums and see what happens. Well, when you look at this, what I'm going to do is use some partial fractions here. So this is n plus 1 times n plus 2. And I'm going to break this up as a over n plus 1 plus b over n plus 2. Okay? Now you're welcome to pause it at this step and figure out what a and b are. But I'm going to give you those values here, right? You're going to get a equals 1, and you're going to get b equals negative 1. Okay? And so let's see what this series does. Let's take a look. So the sum from n equals 1 to, I don't know, how about some capital N? Well, let's see here. So I'm going to write this as so. And then look what happens. 1/2 minus 1/3, right? That's the n equals 1 term. Plus, and then when n equals 2, we'll have 1/3 minus 1/4, right? That's n equals 2, plus all the way up to 1 over n plus 1 minus 1 over n plus 2. Now notice what's going to happen, and maybe I should have written more of these, but I'm sorry, this should be capital N, not capital N. But you've got this negative 1/3 plus 1/3. Negative 1/4, the next one will be plus 1/4. So these you have all these zero sums, and what you're left with is just the first term and the last term, okay? So you can see by rearranging those sums, you get this very nice expression, whoops. And so if I want to know what that sum actually is, right, well, that's going to be the limit as n goes to infinity of 1/2 minus 1 over n plus 2, which is just 1/2. Okay? All right. Well, what about the harmonic series? So 1 over n, this series is known as the harmonic series. And I'm going to prove that it actually diverges. So 1 over n, we know goes to 0 as a sequence, but the sum gets arbitrarily large. And to see this, let's check out some partial sums. So S2 will be 1 plus 1/2, right? S3 will be 1 plus 1/2 plus 1/3. I'm sorry, I don't want S3. I'm doing even sums, plus 1/4. S6, 1 plus 1/2 plus 1/3 plus 1/4 plus 1/5 plus 1/6, and so on, right? And so what I want you to notice is the following. I'm sorry, I'm actually going to use powers of 2 here. Okay. And what I want you to notice is that for S4, this is going to be greater than, and then 1 plus 1/2, and then watch what I do. Right? I've increased the single denominator. And so I've created a smaller quotient here, and therefore a larger sum over here, okay? And then I can play the same game with S8, okay? I can take and say that this is greater than 1 plus 1/2. And then I'm going to take these and call those 1/4 plus 1/4. And then all of these 1/8 plus 1/8 plus 1/8 plus 1/8. Okay? Which actually works out to 1 plus 3/2. Okay? Might be worth noting that this one worked out to 1 plus 2/2. And so if I continue this S2 to the n is going to be greater than, well, 1 plus n over 2, right? 8 is 2 cubed. 4 is 2 squared. 2 is 2 to the first, okay? And so this clearly diverges. If you're adding something greater than 1 over and over and over again, you're going to get an infinitely large number. All right? So the harmonic series diverges. Well, let's think about the geometric series. And you may recall from pre-calculus just what that is, right? You have this series, and it's defined as follows, right? You get from one term to the next by multiplying by r. Multiplying by r. And of course, by the time you get to, you know, from 1 to 30, you've multiplied by r squared, and so on, right? R, of course, is the common ratio. So here's what we have for partial sums, and this is known as a closed form, right? It would be nice to not have to actually physically add terms 1 through 1,000, let's say. It would be a lot easier if you could just tell me you want the sum of the first 1,000 terms and then have some form where you can essentially plug in 1,000 and get the answer. So that's what this closed form is, but let's actually prove it. So the nth sum we know is a plus ar to the first plus ar to the second all the way up ar to the n minus 1. Now, this may seem like a trick, but it works. I'm going to multiply that sum by r. And when I do that, and I'm going to group these terms strategically, right? This first a becomes ar, right? I don't have a anymore. So I have ar squared, ar to the n minus 1, and then when my ar to the n minus 1 gets multiplied by r, I just get ar to the n. And so what I can do now is subtract these, and you get Sn minus Rsn equals, well, gone, 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 gone. You have a minus ar to the n. In other words, Sn factored factor. And so you get Sn equals a quantity 1 minus r to the n all over 1 minus r. Okay, there we go. And of course, now the big question is, under what condition does the geometric series converge? Well, it converges the absolute value of r is less than 1. And furthermore, the limit as n goes to infinity of those Sn's, in other words, maybe I should write it this way, is a over 1 minus r. And again, this should be very familiar, all right? Now we have some nice properties, okay? We're taking the sum of a sum or difference. It's the sums of the sum or differences, right? And the series of a sum is the sum of the series. You factor out constants. But again, big condition, an and bn both need to be convergent, okay? Let's put these into some practice here. Evaluate the series. So the first one, we're going to look at the sum from n equals 1 to infinity of 2 to the negative n. Well, let's rewrite that, right? That's 1 to infinity of 1/2 to the n. And this is geometric with r, absolute value, less than 1, right? But notice it's not quite in the right form yet, right? If I want it in the right form, I need to have that r to the n minus 1. And so if I factor out a 1/2, then I have that. And so we know that this is the limit. And so we have 1/2 over 1 minus 1/2, which equals 1. Okay. All right, let's try another one. Let's try the sum. Oh, that's a horrible sum. Let's do a better sum. Some sums are better than others. Ha, some jokes are better than others too. All right, 1 plus 2 to the n all over 7 to the n. Well, what I'm going to do is break this up, right? Using those properties. 1 over 7 to the n plus 2 to the n over 7 to the n. And then, since those are each geometric, I know individually they exist, so I can actually do this. 1/7 to the n, 1 to infinity, 2/7 to the n. And then just being careful to write things in the correct form before I go on with it. So 1/7 times 1/7 to the n minus 1. And then 1 to infinity, 2/7 times 2/7 to the n minus 1. And so 1/7 over 1 minus 1/7 plus 2/7 over 1 minus 2/7. So what do we get here? We have 1/7 over 6/7 plus 2/7 over 5/7. So let's see, 1/6 plus 2/5, which will be what? 5 plus 12 30ths, 17 30ths. All right. Well, let's go back to our motivation problem now, because what we have is, in fact, a geometric series, right? That's what we actually wind up getting here. So let's take a look and see if we can find that limiting amount. All right. So let's look at let's say the nth day. So on that nth day, we'll call this the amount in the blood. Call it AN. So you're going to have your daily dose, and then you've got the day before, which has been, reduced by a factor of e to the negative k. 2 days before, e to the negative 2k, all the way down, e to the negative n minus 1k, okay? And so e to the negative k is less than 1, so we have convergence, okay? So if I want the limiting amount, the limit as n goes to infinity of this sum, well, it's going to be that initial amount, right? Which was d over 1 minus e to the negative kt, or okay, all right. So there is your limiting amount. All right, so let's talk about convergence, because really at the end of the day, what we are concerned with is convergence, okay? Even more so the existence of convergence than necessarily what the series converges to. So let's take a look at this first. If the series converges, then the sequence whose terms make up the sum of the series, that limit must be 0. Which intuitively should make sense, right? If I'm telling you that the series converges, then that means as I add term plus term plus term plus term, those sums are starting to approach some finite value. Well, if I'm approaching some finite value, the things that I'm adding in each consecutive term should start to get smaller and smaller and smaller and smaller until they're essentially 0. And that's what this theorem says. So let's prove it. I'm going to let Sn be that nth partial sum. So A1 plus A2 all the way up to An, okay? And then I want you to notice that I could write An, or if I solve this for An, then I have Sn minus A1 plus A2 plus An minus 1, which is really the n minus 1 partial sum, okay? Now, here's the kicker. Since An converges, I know that these two partial sums must converge to the same value, okay? So as a limit, what do I know about their difference? Oh, their difference is 0, which will tell me that limit An is 0, okay? So limit as n goes to infinity, An equals limit as n goes to infinity, Sn minus Sn minus 1. And I know that these both exist and are equal. And so we get 0, okay? And that proves it. Well, the natural question is the converse true? In other words, if limit n goes to infinity, An equals 0, is it true always that that series converges? Well, no. And here's your counterexample. The harmonic series. Right? 1 over n goes to 0. But this series diverges. Okay? So the converse is not true. However, this, and I'm not going to actually prove this because it's really just contrapositive, but this is logically equivalent to our last theorem. It tells us a condition for divergence. If those individual, if the limit of the individual terms of the sum is not 0, then we have divergence because we're not adding terms that are getting smaller and smaller and becoming 0. All right, so let's determine a couple. Let's put this into practice. Determine whether the series converges or diverges. So the first one, we're going to look at n equals 1 to infinity, n over 4n plus 1. Well, limit as n goes to infinity of n over 4n plus 1. this equals 1/4, which I really don't care about. What I really care about is that it's not 0. And so this tells me by the nth term divergence test, if you want to call it that, that the series diverges. Now remember, if this limit here had been 0, it wouldn't have told me anything. I would have eliminated, it would have eliminated my ability to decide that it diverges yet, but it doesn't really tell me anything. I have to keep going, do some other work, okay? All right. How about this next one? This next one's an interesting one. Let's look at the sum from 1 to infinity, -1 to the n minus 1 n over n plus 1. Okay? All right. Well, just for fun here, let's look at the odd terms. Okay, the odd terms. Well, so what would the odd terms be? Maybe write out a few just for fun here. Well, here's the deal. N over n plus 1, we know that that goes to 1. And so if we're looking at odd terms, if n is odd, then -1 to the n minus 1 is even. And if it's, well, this will equal 1 since n minus 1 is even, right? If n is odd, then n minus 1 is even, okay? And so the odd terms are going to converge to 1. Well, the even terms, those are going to converge to -1, since -1 to the n minus 1 equals -1, right? N minus 1 will be odd. And so the limit does not exist, and in fact can't therefore equal 0. And so this tells me that the series diverges, okay? All right, so that is a good review of some series and some further discussion, going a little deeper with notions of convergence. I want you to pay special attention to the distinction between the sequence and the series, especially considering the sequence could be converging, but the series may not, okay? And really, at the end of the day, when we talk about the convergence of a series, we're really talking about whether or not the sequence formed by their partial sums converges. And that's what we want to look at. In fact, most of what we're going to do for the next coming chapters, or sections rather, is going to be simply devising tests that we can run to decide if our series actually converges.